On the moon's south pole, there are craters where the sun hasn't hit the ground for millions of years. Temperatures drop to nearly minus 240 degrees C. That's where the water ice is, and it's also where your equipment fails first. This is the part of the moon that looks simple on a map and brutal in real life, not because it's forbidden, not because NASA is hiding anything, because it stacks the hardest engineering problems in one place: permanent darkness, extreme cold, abrasive dust, and power constraints. And if you can't keep machines alive there, you can't keep people alive there either. And here's the strange contradiction that makes the South Pole so important. Those permanently shadowed craters may be the most valuable place on the entire moon. Not for flags, not for photos, for water. In the next few minutes, I'm going to walk you through three things: what these craters are, why NASA and everyone else cares so much, and why extracting ice from permanent night is still one of the toughest real-world problems in space exploration. The moon is supposed to be the easy neighbor. No atmosphere, no weather, no oceans, no biology. Just an ancient world we like to think we've already figured out. We've walked on it. We've brought back rocks. We've mapped it in incredible detail. It feels solved. But the lunar South Pole is the reminder that mapped is not the same as usable. Near the poles, the moon's axis tilt is small. Sunlight arrives at a low angle, skimming across the surface. That creates a weird geometry problem. Some crater walls permanently block the sun from reaching the floor. The result is a permanently shadowed region, PSR, where the ground stays dark all the time. If you've never heard of PSRs before, imagine a natural freezer with the door never opening. No sunrise, no sunset, no seasons reaching the bottom, just permanent night. And the temperature follows. Some of these shadowed areas are among the coldest places measured anywhere in the solar system. Cold enough that normal engineering assumptions start to break. Metals behave differently, lubricants fail, batteries lose performance, electronics drift, mechanisms stick, seals become less forgiving. In that environment, even small failures can cascade. If the South Pole were only cold, it would still be interesting, but it wouldn't be a global obsession. The reason these dark craters matter is what that cold can preserve. Water ice. For decades, the moon was treated as bone dry. Apollo samples looked dry. The surface looked dead. If water existed, it was assumed to be rare and unstable, lost to space over time. That view began changing when missions started measuring the poles properly. NASA's Clementine mission in the 1990s helped confirm that permanently shadowed regions exist. Once that was established, the logic became hard to ignore. If a molecule of water ends up in a place that never warms up, it can freeze and stay there. Then came more clues. Orbital instruments detected elevated hydrogen signatures near the poles. Hydrogen alone isn't proof of ice, but it's an obvious signal that something water-related may be present. Over time, better mapping methods and additional measurements strengthened the case. Today, the mainstream view is that the moon's poles do contain water ice, often mixed into the soil and concentrated in the coldest traps, especially inside and near permanently shadowed craters. On paper, that's a neat science fact. In reality, it's a resource that changes what the moon is for. Because in space, water isn't just water. Water means drinking water. It means oxygen to breathe. It means hydrogen and oxygen you can split and turn into rocket propellant. It means life support. It means shielding. It means you can operate longer without hauling every kilogram from Earth. If you can access and process water on the moon, you stop treating lunar missions like quick visits. You start thinking like an infrastructure builder: bases, refueling depots, and long-duration surface operations. So the obvious question is, if the ice is there, why not just go in and mine it? This is where the moon turns hostile in a way most people never hear about, because it isn't one dramatic danger. It's a stack of practical problems that all get worse inside permanent shadow. First, cold. At temperatures near minus 240 degrees C, your equipment is living on borrowed time unless it's designed for deep cryogenic operation. Heating helps, but heating costs power. Insulation helps, but insulation adds mass. And even when you solve temperature for one component, you still have to solve it for everything: joints, cables, seals, batteries, sensors, tools, and any moving mechanism. Below a certain point, cold isn't discomfort. Cold is failure. Second, power. Inside permanently shadowed craters, solar panels don't help. There is no steady sunlight. That means you need batteries, radioisotope power, beamed power, cables from sunlit ridges, or some hybrid system. Every option adds cost and complexity is the enemy of reliability. This is why many realistic South Pole plans focus on landing and living near the shadow, not inside it, on ridges or plateaus that get more sunlight and have better communications, close enough to reach the resource, far enough to survive. But eventually, if the ice is in permanent night, your machines have to work in permanent night. And permanent night turns space engineering into a different sport. Third, dust. Lunar regolith isn't beach sand. It's pulverized rock created by billions of years of impacts. The grains are tiny, jagged, and abrasive. There's no wind or water to smooth them. Charging effects from sunlight and the solar wind can make dust cling stubbornly to surfaces. Apollo astronauts learned how nasty lunar dust can be even in sunlit regions. It stuck to suits, gloves, and visors. It scratched surfaces. It fouled mechanisms. It got into places it shouldn't. In short missions, that's a nuisance. In long operations, it becomes a reliability threat. Here, what dust does in practical terms. It can jam joints. It can degrade seals. It can coat radiators and reduce thermal performance. It can scratch optics and ruin sensors. It can contaminate connectors and interfaces. A cliff ends a mission instantly. Dust can end it slowly, one weak link at a time. Fourth, communications and operations. Inside a deep crater, terrain can block line of sight. That means communications may rely on relay satellites or carefully designed networks. This isn't glamorous, but it matters. If you can't communicate reliably, you can't operate reliably. And if you can't operate reliably, you can't build anything that lasts. Finally, radiation is the moon-wide constraint in the background. The moon has no thick atmosphere and no global magnetic shield like Earth. That means the lunar surface is exposed to cosmic rays and solar particle events. Radiation isn't always dramatic, but it is always part of the math. It shapes mission duration, shielding, and safety planning. The polar craters don't automatically make radiation worse by magic. The real issue is that permanent night and complex terrain reduce your options. If solar activity spikes, you want robust communications, redundancy, and quick access to shielding. In the deepest shadows, everything is harder: power, movement, and response. So put the whole picture together. Permanently shadowed regions aren't just cold holes. They are places where extreme cold pushes hardware to failure, where sunlight can't power you, where abrasive dust attacks reliability, where terrain complicates communications, and where radiation remains a constant constraint across everything you build. And that, of course, is exactly where the ice is likely to be. This is why NASA's Artemis-era plans and many international plans focus on the lunar South Pole. The strategy isn't march humans into permanent night and dig. The strategy is to build capability step by step. And that's why robots are central to this story. The realistic near-term path is robotic scouting first. Map where the ice is, how concentrated it is, how deep it goes, and what it costs in power and time to extract. You need hard numbers before you build big systems. You need to know whether deposits are patchy or concentrated, whether extraction is feasible, and what kind of processing equipment survives the environment. Concepts like NASA's Viper rover were designed around that idea. Land near the South Pole, investigate volatiles like water ice, and turn guesswork into measurements. Program details and timelines can change with budgets and priorities, but the underlying requirement doesn't. You can't build a lunar economy on wishful thinking. You build it on verified deposits, tested hardware, and repeatable operations. Over the next decade, more missions from more agencies and companies will head toward the poles. They'll sharpen maps, test drilling and sampling, test dust mitigation, and improve power and relay architectures. Each mission will either make the South Pole look more practical or remind us that the hardest problems on the moon are still waiting in the dark. For a long time, we treated the moon like a finished chapter, a place we visited, conquered, and moved on from. But the moon isn't solved, not even close. And the South Pole is the best proof of that, because it forces one simple question: can we operate where the environment never forgives mistakes? If the answer becomes yes, the moon stops being a destination. It becomes a foothold. And that is why the darkest, coldest craters at the lunar South Pole, places the sun never touches, may end up deciding the future of human expansion beyond Earth.